A 1D array is a linear data structure that stores elements of the same type in contiguous memory locations. Basic operations include insertion, deletion, searching, and traversal. Here is an example of an array with elements 5, 9, 3, 1, and 7 stored at indices 0, 1, 2, 3, and 4 respectively. Arrays store elements in contiguous memory locations, and each element occupies the same amount of space. In Python, there are 3 common methods to create an array. Method 1 involves using literal syntax. For example, numbers equals open square bracket 10, 20, 30, 40, 50, close square bracket. Method 2 uses a constructor. For example, numbers equals list open parenthesis range open parenthesis 10, 60, 10, close parenthesis close parenthesis. Method 3 creates an empty array with a specified size. For example, numbers equals open square bracket 0, close square bracket asterisk 5, which creates an array containing 0, 0, 0, 0, 0. As an illustration, if the array contains 10, 20, 30, 40, and 50, these elements would be stored in memory at contiguous locations, such as 1000, 1004, 1008, 1012, and 1016 respectively. Each element is 4 bytes apart. Traversal is accessing each element of the array exactly once. In Python, traversal can be achieved in several ways. Method 1 uses a for loop with indices. For example, for I in range open parenthesis len open parenthesis numbers close parenthesis colon print open parenthesis f open quotation mark element at index open curly brace I close curly brace colon open curly brace numbers open square bracket I close square bracket close curly brace close quotation mark close parenthesis. Method 2 uses a for each loop. For example, for value in numbers colon print open parenthesis f open quotation mark value colon open curly brace value close curly brace close quotation mark close parenthesis. Method 3 uses a while loop. For example, I equals 0, while I less than len open parenthesis numbers close parenthesis colon print open parenthesis numbers open square bracket I close square bracket close parenthesis I plus equals 1. For example, if we consider an array containing 42, 17, 29, 35, and 89, traversal involves accessing each element in sequence. The time complexity is order of n, and the space complexity is order of 1. Traversal follows a sequential access pattern and is a foundation for many array algorithms. Array insertion involves adding a new element to the array. Here's how it works. In the original array we have 10, 20, 30, 40, and 50 stored at indices 0, 1, 2, 3, and 4 respectively. Now let's insert 25 at index 2. The new array will be 10, 20, 25, 30, 40, and 50. Note that the elements 30, 40, and 50 have been shifted to accommodate the new element. In Python, to insert at the beginning, we can define a function insert beginning open parenthesis array element close parenthesis colon return open square bracket element close square bracket plus array. To insert at the end, we can define a function insert end open parenthesis array element close parenthesis colon return array plus open square bracket element close square bracket. To insert at a specific position, we can define a function insert at position open parenthesis array element position close parenthesis colon return array open square bracket colon position close square bracket plus open square bracket element close square bracket plus array open square bracket position colon close square bracket. Time complexity at the beginning is order of n as we shift all elements. At the end it is order of 1, which is constant time. In the middle, it is order of n minus k, where k is the index at which we insert the element because we shift elements after k. Space complexity is order of 1. The function insert at index takes an array, an element, and an index as inputs. Step 1 involves creating a new array with a size 1 larger than the original array. Step 2 involves copying all elements up to the insertion point from the original array. Step 3 involves placing the new element at the insertion position. Step 4 involves copying remaining elements from the original array with an offset of 1. Therefore, the function would be like define insert at index open parenthesis array element index close parenthesis colon new array equals open square bracket 0 close square bracket multiplied by open parenthesis len open parenthesis array close parenthesis plus 1 close parenthesis. Then, for I in range open parenthesis index close parenthesis colon new array open square bracket I close square bracket equals array open square bracket I close square bracket. New array open square bracket index close square bracket equals element. Then, for I in range open parenthesis index comma len open parenthesis array close parenthesis colon new array open square bracket I plus 1 close square bracket equals array open square bracket I close square bracket. Return new array. For large arrays, this operation can be expensive due to shifting elements. Therefore, it's advisable to use built-in methods like insert, open parenthesis, close parenthesis, for better performance. Array deletion involves removing an element from the array. Here's how it works. In the original array we have 10, 20, 30, 40, and 50 stored at indices 0, 1, 2, 3, and 4 respectively. Now let's delete the element at index 2, which is 30. The new array will be 10, 20, 40, and 50. Note that the elements 40 and 50 have been shifted to fill the space left by the deleted element. In Python, to delete the first element we can define a function delete beginning open parenthesis array close parenthesis colon return array open square bracket 1 colon close square bracket. To delete the last element we can define a function delete end open parenthesis array close parenthesis colon return array open square bracket colon -1 close square bracket. To delete at a specific position we can define a function delete at position open parenthesis array position close parenthesis colon return array open square bracket colon position close square bracket plus array open square bracket position plus 1 colon close square bracket. We can also use the built-in method delete using pop open parenthesis array position close parenthesis colon array dot pop open parenthesis position close parenthesis return array. Time complexity from the beginning is order of n as we shift all elements. From the end it is order of 1 which is constant time. From the middle it is order of n minus k where k is the index from which we delete the element because we shift elements after k. Space complexity is order of 1. The function delete at index takes an array and an index as inputs. Step 1 involves checking if the index is valid, that is, within array bounds. Step 2 involves creating a new array with a size 1 less than the original. Step 3 involves copying all elements before the deletion index. Step 4 involves copying all elements after the deletion index with an offset. Therefore, the function would be like define delete at index, open parenthesis array index close parenthesis colon. If index less than 0 or index greater than or equals to len, open parenthesis, array, close parenthesis, colon, return, open quotation mark, invalid index, close quotation mark. New array equals open square bracket 0 close square bracket multiplied by open parenthesis len open parenthesis array close parenthesis minus 1 close parenthesis. For I in range open parenthesis index close parenthesis colon new array open square bracket, I close square bracket, equals array, open square bracket, I close square bracket. For I in range open parenthesis index plus 1 comma len open parenthesis array close parenthesis colon new array open square bracket I minus 1 close square bracket equals array open square bracket I close square bracket. Return new array. Deleting from the beginning or middle requires shifting elements. Therefore, it's advisable to use built-in methods like pop, remove, or slicing for better performance. The goal of searching is to find a specific element within an array. One common approach is linear search. In this method, we check each element of the array one by one until we find the target element. The function linear search takes an array and a target as inputs. For example, define linear search open parenthesis array target close parenthesis colon. For I in range open parenthesis len open parenthesis array close parenthesis colon if array open square bracket I close square bracket equals target colon return I. Return -1 foot. For the example array which contains 15, 42, 7, 23, 91, 33, 58, if we are searching for the element 23, the algorithm checks 15, 42, 7, and then finds 23 at index 3. Time complexity is order of n, as we may need to check all elements. Space complexity is order of 1, as no extra space is needed. Advantages of linear search include simplicity and applicability to unsorted arrays. Disadvantages include inefficiency for large arrays. The best case is order of 1 when the target is at the first position, and the worst case is order of n when the target is at the last position or not found. Binary search is another algorithm used to find a specific element within a sorted array. In this method, we repeatedly divide the search interval in half. The function binary search takes a sorted array and a target as inputs. Define binary search open parenthesis array target close parenthesis colon low equals 0, high equals len open parenthesis array close parenthesis -1. While low is less than or equals to high colon mid equals open parenthesis low plus high close parenthesis flow division 2. If array open square bracket mid close square bracket equals target colon return mid, else if array open square bracket mid close square bracket is less than target colon low equals mid plus 1 else colon high equals mid -1. Return -1. For the example array which contains 10, 15, 23, 31, 42, 58, 67, if we are searching for the element 42, the algorithm first calculates the middle index. Since the element at the middle index, which is 31, is less than the target 42, we search in the right half. Time complexity is order of log n due to the divide and conquer approach. Space complexity is order of 1 for the iterative approach and order of log n for the recursive approach. The array must be sorted. However, it is much faster than linear search for large arrays. Here is a summary of the 1D array operations we have discussed. Traversal involves accessing each element exactly once, is foundational for other operations, and follows a sequential access pattern. Time complexity is order of n, and space complexity is order of 1. Insertion at the beginning requires shifting all elements, at the end is a constant time operation, and in the middle requires shifting elements after the insertion position. Time complexity is order of n, and space complexity is order of 1. Deletion at the beginning requires shifting all elements, at the end is a constant time operation, and in the middle requires shifting elements after the deletion position. Time complexity is order of n, and space complexity is order of 1. Searching can be performed using linear search on any array with the time complexity of order of n, or using binary search on a sorted array with the time complexity of order of log n. Built-in methods include index and find. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.